Hello, my name is Ryan Majinski, and I am studying the asymmetric synthesis of the anti-cancer agent Elacomine under the supervision of mentor Mamoun Hussain and graduate student Shahnawaz Ali. Elacomine is a compound made naturally by certain shrubs of the Elagnus family, which is related to the more commonly known silverberry plant. Looking at the graph under the introduction on the lower left side, the agent Elacomine kills numerous types of melanoma cells, which cause skin cancer, reducing their cell viability to under 25%. However, it does not kill normal human cells, which provides an extremely targeted and theoretically safe approach to curing melanoma skin cancers. Unfortunately, this drug is not commercially available, and we believe this is in part because of the current lack of an efficient total synthesis and the difficulties of isolating a compound from plants in mass quantities. The Hussain laboratory has successfully created a full synthetic route for the analgesic agent coarelecin. Looking at the second image in the second column, the two molecules coarelecin and elacomine have very similar substructures. We hope to use the synthetic route our lab created for coarelecin and apply it to elacomine. In more common terms, this would be similar to modifying a chocolate chip cookie recipe to instead make peanut butter cookies. We will be making a similar cookie, but we will change some of the ingredients to create a completely different taste, even though we followed similar steps. In our case, we need to use a less reactive starting material, so we will adjust each step individually to optimize the yield and purity of the final compound. The first step of this synthetic route uses a reaction first developed in the Hussain laboratory in 1998, and you can see the scheme and mechanism of this reaction at the bottom of the second column. In this case, we wanted to apply the reaction to a broader array of starting materials than had originally been studied, so the Hussain group investigated the full scope of this reaction to form a wide array of 3-hydroxyacrylic acid esters. Table 1 in column 3 includes some of the research I personally performed during this investigation. At the conclusion of this study, we confidently knew how to apply this reaction toward the first step of forming elacomine. The second step involves the formation of an all-carbon quaternary stereocenter, in which 4 different functional groups are all attached to the same carbon atom. This is difficult to make because of the close proximity of the bulky groups, so I have again begun the process of optimizing the reaction conditions using the specific reagents needed to form elacomine. These preliminary results are summarized in Table 2 in the 4th column. More work is needed to further optimize this reaction and then proceed with the last 4 steps. At the conclusion of this, we aim to have an efficient method of forming elacomine with the hope that it will one day be commercially available as a treatment for skin cancer. Thank you.